Well, looking back at Popular Chris, I'm going to do my lecture today in the Scots accent. So, if you have a problem with that, well, I just have to clap in me wall in a blare and market whistle and legs and arms and heads a snare like taps a thistle. Sorry about that. Good morning. Welcome back. Hey, that was fun. That's a bit of a line from Robert Burns, in case you're curious, a haggis. I'll do the whole thing for you if you'd like, and of course it has to be done in Scots. It just doesn't work if you do it in English. I'm not English. I'm Welsh, which is a Celtic tribe, much like the Scots. Actually, are they Celtic or Picts? Well, anyway. Okay, my least common ancestor is from Wales. Oh, sorry, we're on the wrong topic. Sparse matrices. Remember now, we've got least common ancestor, path decomposition, the first descendant of a node, level, and the skeleton matrix. Okay, it's a mouthful. So I want to do two things today. Hopefully wrap up the row count algorithm. It's like we've been doing this forever, counting. And then I want to talk about the next project as well. So I'm meaning to pause in the middle and talk about that. So the where we left off, we've got this notion here. We've got the post ordering, so we can look at a leaf and know when it is look at a node and know when it's a leaf and when it's not. And we've got this algorithm here. Now this is a bit of a twist, but the idea is that we exploit that first descendant, and we're going to walk across the leaves. Walk across the non-zeros in A, and then we have a test here now that tells us quickly. And forget the I for the moment. Okay? Imagine we're just stuck at row I. So you notice this loop is reversed. We're going down J, not I. So transpose this algorithm in your head, and you'll get what we had before. Walk across row I, and if you're on the ith tree, if the first of J, the node you're at, is larger than the biggest first you've seen so far, then you have a leaf, and update the max first of the ith tree. And if you're just living on the ith tree, there's no need to say max first of the ith tree because that's the tree you're working on. Okay. This algorithm, though, doesn't just stay at one tree. It's going to look at a whole pile of trees all at the same time. And it's going to go down the columns of the matrix for J, one at a time. Then it's going to operate on the ith trees for all I that node J exists in. So we've got a whole pile of trees. Here, for instance. So if J is, say, equal to 7, so suppose I'm going through, here's the skeleton matrix. Well, here's the skeleton matrix that ignores these circles. Suppose I'm going through, let's pick a column 7. Okay, then I've got two trees to look at. And I want to look at node J in whatever tree it's going to exist. In particular, that's going to be this one, no, 9 and 10. Here we go. This one and this one. That's the only place I have to consider the question, is 7 a leaf of a tree in which it resides? Tree, because you only have to look at the non-zeros in the column of A, so these two, and ask the question, is that in the skeleton matrix? Is that in the skeleton matrix? Well, this one is, because you see it's a leaf. And this one is not, because, oh, look, it is not a leaf. Now, we don't need to consider, say, this node, because that's not non-zero in A at all, so it's certainly not in the skeleton matrix. This right here. It exists here, because it's filled in L, because it's in the tree, so it's in L. That entry. That's that right there. Node 7 is in the 8th tree. There's the 8th tree right there. It's got 3 nodes in it, the root and these two, 5 and 7, 5, 7, 8. Okay, so but in row 8, the only non-zero in A, in fact, is just one of them, 5, and so that's a very simple case. So we want to take this max first algorithm, looking for leaves, looking for skeleton matrices, looking for the skeleton entries, transpose it on its head. So we're going to be going through column J and then asking, for all the trees that node J is in, are you a leaf? Okay, so it just flips the algorithm in your head. And this is, again, where it helps to be dyslexic like I am. Dyslexia is a good thing. So the reason we want to transpose this on its head is for the next thing, this least common ancestor. This least common ancestor idea is the trickiest one of them all. To compute efficiently, I should say. It's very easy to compute if you have enough time to compute it. And let me explain why that's easy. So here's the notion, and here's you first have to understand what's the best way of what's a least common ancestor mean, and then what does it mean in a post-ordered tree? That's very important. And then from there, how can we compute it efficiently? And we're going to again use this disjoint set union find method that we used for the E-tree computation in the first place. We use it again here. Okay, but it's one thing at a time. So the least common ancestor is that node C that if you walk the path, it's the lowest node in the tree that's the ancestor of both of them. So any one up here, for instance, well, that's not a least common ancestor. This one is. All right. In genealogy, it's called the most recent common ancestor. That's why I dropped into my Scots this morning. You missed it if you came in late. You'll have to watch it on tape. It's, huh? It's totally worth it. Yes. Well, so that's least common ancestor. Now, in a post-ordered tree, there's a very easy way of finding this without having to traverse both paths. We only have to traverse one of them. And here's why. In a post-ordered tree, think of this node D. Okay. In a post-ordered tree, D is going to be bigger than C. Now here's where dyslexia hurts you. D is less than C, I said. So C is less than D, and these nodes are all ordered like this. And there's other nodes in the middle there. In fact, inside this inequality here are not necessarily all the descendants of D or C, but certainly all of them that are along this diagram that I've drawn. In fact, you could have other descendants out here, okay, that are D could look like this. So I've only drawn these 4 nodes. So let's ignore that for the moment. So I've got A and B, and I want to find who is the least common ancestor. LCA of A and B is what I'm trying to equals what? Well, it's equal to C. So how do I know it's equal to C? Well, think of this. Think of traversing this graph. And let me put in some actual nodes here. So I'll call this node E. Okay, what's the property of node E and C and D? We want to walk this path here and be able to detect, yes, I found it. That's the least common ancestor. Well, they do all have the first, but so does D. So it's all A. The first descendant, not necessarily actually. They could have different first descendants. So no, that doesn't help because I could have E could have the first descendant of A, but C could have another child out here, which is node 0. So no, that doesn't help. The first descendants doesn't help, but very good, thinking. You're moving in the right direction. No, it's just based on the node numbers. So it's based on this inequality. So watch this right here. So I've got A less than B, less than. Let's see, where is E is going to be less than B. If I come to a node E, E is going to be E has to be less than C. I know that much. I don't know if I want to compare, if I care to compare E and B to, yeah, I do. E is going to be less than, B is going to be less than C. E is going to be less than B. And I know that because if it's not the least common ancestor, if you're going from left to right in a post-ordered tree, B is not the descendant of E, but it comes afterwards, so it must be numbered larger than E. Okay, so here's the tree. The tree for E includes A, but not B. So it must have come, because A comes before B, E must become before B. But now think about what happens when you jump to C. Now you're walking up this path. You see node A, you see node this, you see node, you see node E. You can do this test. Oh, well, E is less than B. So I know that that is not an ancestor of B. Then when I come to C, I see this node, and I say, oh, look, suddenly, and I'm always comparing with the node B. All of these nodes here are numbered less than B, and all of these nodes are numbered bigger than B. So you just walk up the tree until you find a node. You've got A and B, you know A and B. You start at A, you walk up the tree until you find a node number that's numbered bigger than B. And the first one that is numbered bigger than B is your least common ancestor. There you have it. So we've cut out half the path traversals. We only have to traverse this path once. If all we had to do is one least common ancestor computation, then we just have one path to follow. All right? But now, and so this is helpful. Cuts the work kind of in half if the tree is balanced. And got lots of pairs of nodes, A and B and A and B and A and B. But now, what if we've got lots of these least common ancestor computations to compute? And we're going to have a lot of them, because each of these trees, every time you see these nodes merge, I mean, we have a node with two children. I've got a path decomposition there. I've got multiple paths here. There's 3 paths. There's the number of disjoint paths is equal to the number of leaves, right? Because I've got 3 here. I've got 1, 2, 3. I've got to keep finding these. I've got to find least common ancestors of every pair of leaves. 2 and 3 is 4. And so that says that the first path goes all the way up to here. The second path stops just before 4. And the least common ancestor of 3 and 8 is 10. So that means that the path starting at 8 is going to stop just before 10. And that will determine my disjoint set of paths. And once I have the disjoint set of paths, I know where they start, where they finish. Because when I know where they finish with the least common ancestor, I know their length because I know the level of all the nodes. I know the length of the path without traversing it. So how can I find, the only thing left then is how can I find the least common ancestor efficiently? And I cannot afford to traverse these paths. At least more than once. I don't want to traverse them over and over and over again. Well, this is where turning the problem on its head really helps. This is where going through all the trees, so going down the column of the matrix, we're going to go down the column of this matrix and go through all of these trees in which we find entries. So what's happening then, we're at a node J, and we're at a node J in a tree Ti, and another tree Ti, we're at a node J, or a different I, I1, I2, and we've got another tree here, a subroot, this should be a superset, not a subset, T sup I2, T sup, what is tea soup? Is that green tea or black tea? I don't know. Kombucha maybe? Node J. T superscript I3 and so forth. We've got all these different trees. So if we walk down, I don't have any case where I'm in 3 trees, do I? But oh well. So I go down here and I say, well, let's look at these 2 trees. And let's look at node 7 in each of those trees. So now, what is it we have to do? We have to compute the least common ancestor of some previous node in here and another previous node in here. I'll call this J previous. This is J. This is the previous leaf. It's the last leaf I saw. And if there was no last leaf, then it's simple. It's the very first, the very leftmost leaf, and the path, there is no path decomposition needed. It's just, there you are, you're done. It's only the case where you have a subsequent leaf that you need to say, well, what's the previous leaf? What's the current leaf? We know how to find the leaves now with that max first notion. So we look at a J and say, yes, really quickly, I know in constant time, you're a leaf of the skeleton matrix. And then find the least common ancestor, and then if I can do that in constant time, I know the path lengths and I'm done. So 2 and 3, I need to do this, and then 3 and 8 and so forth. So consider, say, node, and unfortunately this is a very simple matrix, so it's kind of hard to see. But let's suppose it's node 6. That has 2 leaves, or maybe node 5. Is that interesting? No, that's kind of boring. I guess node 6 is the most interesting node here. Node 6 is a leaf here. See those 2 black dots? The circles are non-zeros in A, but they're not in the skeleton matrix. So let's look at these two. 6 and 10. I'm sorry, column 6 in trees 7 and 10. So let's look at this node, and let's look at this node right here. So the J previous of this will be, I'm going to change this to a 6 here. 6, and this is a 5, and this is a 6, and this is a 2, right? Yeah. So I've got to find the least common ancestor of 5 and 6, and here I've got to find the least common ancestor of 2 and 6. So I've got to start at 2 and walk up the tree and stop if I see a node bigger than 6. I've got to start at 5 and walk the tree until stop when I find an ancestor bigger than 6. So here I go up and I hit 10. Here I go up and hit, and so forth. Actually, so here. Now, but as this computation goes on, we've already done the columns to the left of us. So they don't need, whenever I'm doing this least common ancestry question, it's always, the last argument, it's always J previous and J that I need to find now. Where this is smaller than this. And once I compute all of the least common ancestors between some previous node and J, then J won't appear here again. Because J will be incremented to the next column, into the next column, into the next column. And so think about what's going on here. This is always a new entry. This is always something new. This is incrementing, J++, going to the next column, the next column, the next column. But this one right here is always an old thing. You've seen this before, perhaps. This is how we're going to speed it up. So always computing the least common ancestor of something old and something new. There's a wedding thing that goes like that, right? You're always supposed to bring something old and something new. This is the something new. This is the something old here. And now what is it you're doing with the something old? You're having to walk a path. And then you stop where? You stop at a point until you see a node bigger than J. Well, as you walk, so the next time you do this, you've got an old thing, you walk a path. You've got an old thing, you walk the path. Gee, I've walked this path before. I'm really sick and tired of walking this path. I start the same old thing and I walk up the same old path. I'm getting real tired of this. Can't I find a shortcut? Because look what's happening. Look what's happening. You're always going to stop at a new column that's getting bigger and further away. So the first time you walk the old thing, you go dum, 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 stop. Okay, here I found it. Okay, second time, I see this old thing again. And now J is bigger, so you got to walk farther. Dum, 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 dum. Hey, wait, I just walked this before. And then you go a little bit farther. Oh, look, here's my answer. Okay, boy, that was a lot of work. And now you do the same thing again. You've got your target is a bigger J, and you start the same old thing, some other previous leaf. I just walked all this before. Oh, here I am. Well, if you keep walking that same path over and over again, make yourself some shortcuts. That says, well, look, I started here. If I start here, I know I'm going to at least get that far. You missed that on tape. I'm going to at least get this far. So make myself a shortcut. That's the disjoint set union find. The idea is if you're in a subtree, okay, and here's the old thing. And your target is some node that is just bigger than J. Well, all of these are going to be less than J, right? That's what I showed you here. So it's like, well, this is the old thing. You keep walking the same old path. So no matter which path you walk across this pile of subtrees, this subtree here, you're always going to end up at the same place. That's your ancestor. Not your least common ancestor that we're trying to find so far. Okay? But that is instead... Oh, I might have hurt something. I've been having back problems. I should not have jumped. Okay. We can think of this subtree here as just a single blob. If we could somehow magically collapse that into a single set with one master, we meet again, Obi-Wan. Only I am the master now. Okay, with one master over them all, one master to rule them, and in the darkness bind. Oh no, that's Lord of the Rings. Wrong master. I'm mixing my movie metaphors here pretty horribly. So we've got this root of this set, and then the next time we see this set, I'm going to perhaps go a little bit farther. But every time I go a little bit farther to just before a least common ancestor here, so here's my least common ancestor that I will have found, C. I don't want to put that in my set yet. Okay, this is the C that's bigger than both the old thing and J, which I'm now calling, I called it B over here. I should have called this J. But this node E here, if I ever see one of these old things again, I'm going to hit E, because I'm always going to ask the question, see, J is incrementing. It's only getting bigger. It's only getting further away. So you're only going to walk farther. If you're always going to walk farther, you're always going to see node E. If you're always going to see node E, just give everybody in this tree the shortcut to node E and get there in a single hop. Makes sense? It's a shortcut. And so every time you walk across multiple nodes, okay, update this shortcut. Now there's one twist here though, is that we don't know where we're going. See, with the elimination subtree, I'm sorry, not with elimination, with computing the elimination tree in the first place, we knew that no matter how we started, we were going to hit node K. We're walking up here, we're going to hit node K. And then every time we walk again from that path, we'll see node K and then an ancestor. So we know the most distant ancestor already, in that case. So in the elimination tree algorithm, let me go way back here. Computing the tree. Oh, I went too far. Here. See this ancestor idea. Now this is not computing for us the least common ancestor, but it's keeping track of us this master of the subset idea, the master of the subtree. I know where I'm going to go. This is my shortcut. I know I'm going to hit node K without even having to traverse it twice. So just, this is my shortcut. Wherever you are, K, that's my shortcut. Okay? So this path does not have to be traversed twice. But here, we don't know, when we start at A, we don't know where necessarily node E is going to be. Because A might have the notion that its ancestor is here. And we don't know E yet. And this node, so we hop across a shortcut here, so we cut off 20 nodes. But we only get part way. So this cuts another, we have another shortcut that maybe gets us the rest of the way. So this collection of shortcuts, you know you're going to reach node E, but you don't know you're going to reach node E. I mean, you know you're going to reach this node, but you don't know its name yet. So as we're traversing these nodes, we can't say, well, I'm going to get here and just point it to, I have to traverse this path, but I have to, well, actually, in the elimination tree algorithm over there, this is, if you will, node K. Node K is my ultimate target. And in that algorithm here, as I'm walking up here, everybody's going to point to K, because I know that's where I want to go. But I still have to traverse this path, because I'm still trying to find this node E. This is I now. This is the node just before. I don't know node I. You see, this is the node I who I need to change the parent of. I know I'm going to reach K, but this node I for which I've got to set the parent, I do not know. That's like the node E that I drew over there before. So I'm reusing these numbers here. Here's the node, here's the last I, and here's the K in that algorithm. So I've got to find the I. I don't know where I is, but I do know K in this method. K is actually the least common ancestor of these two leaves. But in this case, I know K. That's the root. It's not a least common ancestor. I'm not computing least common ancestors over here. Okay. But it is the target of my traversal. It's the target of the path. It's K. So I know where I'm going with K, and so I can set my shortcuts as I make these hops. I've got to find I, so I still have to I still have to traverse. But as I make these hops, all the nodes I see, the ancestor is set to K. But over here now, in this algorithm, to traverse these, find these least common ancestors, I do not know my target. Let's see. So I've got to keep track. So once you traverse this and you find, oh, there's node C, well, you got to go back over this. You got to traverse it twice, not for you, not for your benefit, because you've already gotten to your end goal. But the next person who's going to walk along this trail, it's like little the Hansel and Gretel, walking through the path, dropping breadcrumbs. We're going to drop little breadcrumbs along this path to say, oh, you can take a shortcut and avoid the big bad wolf and go straight here to node E. So in fact, the shortcut is not going to be to K, it's going to be to E that I want to keep track of. So that's the, and I'm going to walk through with you an example, but let me show you the code here then. So this is not the entire row count algorithm. It's on 2 pages, but it's one function that fits on 1 page. So I tried to break it up so it fits. We have to keep track of multiple things here. So there's 5n workspace now. It's getting rather complicated. I guess the complexity of the algorithm, the complexity intellectually of the algorithm increases with the square of the number of workspaces. Okay, so there are a total of 5 workspaces. This ancestor is going to keep track of the shortcut. Max first, which is going to help me find my skeleton leaves. The previous leaf, because for every tree I've got to know who my last leaf is. Because see, there's a previous leaf that's different for every tree. The first of every node, which is computed once and then statically reused. And the level of each node, which is also computed once and then reused. And then there's a 6th data space, which is the actual row count, which is our result when we're trying to compute one collection of n integers. It's that hard to compute. So we already showed you this algorithm. Find the first descendant using the elimination tree. The elimination tree is input to this algorithm, and so is the post ordering. These are inputs. Given the parent and the post ordering and the A matrix, compute the row counts. So with the parent and post, find the first and level. You'll notice, by the way, that this function does not have CS underscore in front of it. So this is not actually part of C-Sparse, because there's yet another algorithm which is going to encompass this and do yet more. But I had to make this more manageable. This is, if you will, it's already a big chunk to bite off of. intellectually. So it's the biggest chunk in the book here, intellectually, to comprehend. But yet there's one more piece to it, is the column counts, not just the row counts. So the row counts are easier. The row counts start out as 1, and that counts the diagonal entry, because that's not going to be in any path at all. And initially, every node is in its own ancestral clique. Every node is its own ancestor. I'm my own grandpa. Okay? If you know that country music song. Okay, now I'm going to go through every column J, and you can ignore the K and J distinction here. If you imagine that the matrix is already post-ordered, you just go through J from left to right. Okay, so this is just a viewing the matrix through that lens. Or you know how to handle that. So ignore this issue. Imagine we're just going J++ here. You notice over here I didn't worry about J versus K. it's post-ordered. You know, you have to take these in bite-sized chunks. So just imagine we're going across J. We go down the column, grab a node I, and then do this traversal question. I've got the previous leaf here, and I've got the current leaf. If it is in fact a leaf, I'm going to check that. And if it is a new leaf, I'll go with the old leaf. I'll find the least common ancestor. I'll do the path shortcut business to help the next guy. And then I will determine the length then. The goal here is I'm at a node J, and I have a previous node here, which I've already accounted for. I've counted that path. I've counted the nodes in that path before. I have to find this least common ancestor, I call it Q, so that I know about this path. Once I know that path, once I know Q and J, then the length of this path is just the difference of the levels. So that's what this down here. If I really did, J leaf is returned true if J is in fact a leaf. I probably should have changed the word J leaf to J is a leaf, or is a leaf J or something. And if it is, I just increment the row count by the differences in the levels. And then I need to take node J and make its ancestor the parent, because that's a minor twist. Because I know that's going to be, let's see, that's a minor twist to the way the algorithm works. So let me, so when I'm looking at the leaf then, asking the question, is it a leaf? So this is this skeleton matrix algorithm. Okay. First of all, I may actually have been given an upper triangular matrix. I'm only interested in looking at the lower triangular part. So if I come across an entry in the upper triangular part, well then this whole algorithm is pointless. I'm not even anywhere near part where I want to compute, so I skip it. Otherwise, if first of J is larger than max first, then it is a leaf and I've got work to do. Otherwise, if it's less than max first, there's no work to do. It's not a leaf. So kick out and done, return false, J is not a leaf. -1, there's actually 3 states that are returned here. -1 means it's not a leaf. But I have to know whether or not it's the very first leaf of the tree or whether it's a subsequent leaf. If it's a subsequent leaf, then I've got different work to do than if it's a first leaf. So if it's a first leaf in the tree, if there's no previous leaf in the tree, then I have no work to do. I don't have to traverse the path. I already know the answer. The root of the ith subtree is I itself. It's easy at that point. If I'm at the ith subtree and I have the very first leaf, well, that's where I'm going. I don't need to do anything. So there's no least common ancestor computation at all. So I can't start this shortcut business because there's no shortcuts to make. There's no pair of least common ancestors to compute. So just return. Otherwise, I've got to traverse up this path and I take advantage of the shortcuts. So this algorithm would operate, it would work, it would just be slower. If you take out the word ancestor and put in the word parent, doink, 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 it would work. And then you could skip this whole loop right here. You could just delete the word ancestor, ignore that array entirely, replace the word ancestor with parent, and the code would work. I think. I haven't tried it, but it should. But we're going to, instead walking up parent, 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 we're going to go ancestor, ancestor, and go far. But then when we're done, we find out, now I know where I'm headed. I'm headed to node Q. That's going to be now my ancestor is Q. Because the next time I traverse a path, I know I'll at least find Q, and I'll need to go go farther. And the root of the tree in this case is denoted. This is why the previous statement with setting the ancestor equal to the parent. The root of this tree is noted slightly differently than the E tree. The root of this ancestral tree is denoted by the fact that you're your own grandpa. You're your own ancestor. So there's a self loop at the very top of each ancestral tree. Shortcuts. If you find a shortcut to yourself, then that says you've reached the end. So this starts at the previous leaf, walks up, stops until it finds itself, finds that it's terminated, and that's the most distant common ancestor. So that's the row count algorithm, and I have a full-blown example that I'll post on the web as well. And if I have time, I'll go through it. I basically walk through with this. I think it's helpful because I came back at this algorithm a year or two after I wrote the book, and I'm trying to decipher what it's doing. What is the intent of the author here? And so I made up this little, 3 or 4 page step-by-step trace of what this row count algorithm is doing on this specific tree. And it's very helpful, I think. So I'll scan it in and I'll post it on the web, but I will also walk over the example in class. But that's the row count algorithm minus the last example because I want to have a little time to look at the next project. This is going to be for the next project. Although this is a little bit more powerful than what I actually need for the next project. With the next project, we're going to backtrack just slightly, but we're going to use a different theorem. Remember the theorem that said if you've got I and J, and I is a child of J. That is, J is equal to parent of I. Okay. Then the following thing happens. You could have the following. You could have a 0 here and a non-zero here in a particular row I. That's certainly possible. However, if you have a non-zero here, then that induces the non-zero there. I mean, that's because of the sparse triangular solve in computing the kth row, or the ith row, if I want to call this I. Okay, that was a very simple theorem we looked at a while ago. Now, so think about what that means. So that's talking about the row, but think about what it means for these two columns, I and the parent of I, J. What this says is this means it's a subset relationship. This means that this pattern right here is a subset of this pattern right here. So if I call this entire, if I use script L sub I to denote this entire thing, including I itself, if I take L sub I, and I know that J is a parent of I, then L sub I minus I itself is always going to be a subset of Lj. So this is important. Now, the question that we can ask is we can use this subset relationship to speed up a triangular solve with even a dense right-hand side. Let me show you what that algorithm looks like. So there's something interesting about this relationship here. Think of how many non-zeros are there in each column of a matrix. You know that right away. You can look at the column and take the difference of the column pointers and say, well, that's how many non-zeros there are. You don't actually have to look down the entries and count them. You know in the data structure how many non-zeros there are. So this is very easy. We have this information in constant time. Let's add another constraint. Let's suppose that I plus 1 is equal to j. We're looking at two adjacent columns in the matrix, I and I plus 1. So they're next to each other. And we know also we can do a quick test to say, hey, the parent of I is equal to j. The parent of I being equal to j is actually easily found without even looking at the elimination tree. We can actually look at the matrix L itself with two assumptions. If I store L in column-oriented form, that's a pretty simple, the three assumptions. If I store L in column-oriented form, just a compressed sparse column matrix, and if the row indices are sorted, I can look at the second entry. That's the parent. But that assumes that I didn't have numerical cancellation and MATLAB didn't delete it on me. Nuts. MATLAB does that, doesn't it? MATLAB stores it in compressed sparse column form. It stores the matrix with sorted row indices, and numerical cancellation hardly ever occurs. But when it does, this assumption is broken. Nuts. But for the project, we're going to live dangerously. In other words, we're going to assume that numerical cancellation does not actually occur. So this entry will be there. Okay. So let's suppose we ignore, if we ignore it like in C-sparse, we ignore numerical cancellation. And C-sparse, in the Cholesky factorization, this is the Cholesky L. The Cholesky factorization does produce L with sorted row indices because it computes it one row at a time. And then sticks the entries in the columns that they exist. They appear. So all the assumptions work beautifully for C-sparse. It's just that MATLAB mangles it a little bit. Let's assume for the moment that MATLAB and C-sparse are cooperating and MATLAB does not drop this entry. Then it's very easy, even just looking at the matrix L, that says, I know who your parent is. So you can look at two rows I and J next to each other, and you know right away, we can look at any two, you can look at any column and find its parent. So finding the parent's easy. Finding the counts are easy. Now, and this is always true, well, except for numerical cancellation, right? Because it's possible that this entry could numerically get canceled, and then so this is broken. Again, we have to ignore numerical cancellation for this theorem to be true. Do you see what happens with numerical cancellation? You throw away zero entries that are numerically zero, but they're symbolically present. You break all the theorems. You don't have a Cholesky L anymore. You've got a general L, and you can't use the tree. You have to use the DAG, and you have to do all the theory breaks. But let's suppose we ignore cancellation. What happens? Think about the extreme case in here. This is a subset here, which means it's not necessarily a proper subset. You see this notation here. It could be that there is no such row I where it's 0 here and non-zero here. In other words, it could always look like this. They could be identical. So how do we know it's identical? Well, if these are equal, then the size of this set will have that property. Because we know I cannot appear in J because it's above the diagonal. See, I've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 4. So I have a constant time check. If I'm at a column I and a column I plus 1, and I can do this, if I look at column count I minus 1 is equal to column count of I plus 1, and looking at the fact and checking to see is the parent of I equal to I plus 1, then I can make a very important conclusion. I can conclude this set relationship without testing it. I can conclude over here that the two sets are equal, excluding I itself. What's so useful about that? Imagine you're doing a triangular solve. You're going through a forward solve, I plus 1, and so forth. You're doing I plus plus. You're looking at columns I. Well, I should have used J, I guess. J and J plus plus. I'm sorry. Because I usually use J for columns, I for rows. But you're walking across the columns one at a time. And you come across and you check this condition. Suppose you check this condition for 2 columns in the matrix. Can you think about how you might be able to exploit this to speed this algorithm up? What's that? You're at 2 adjacent columns. What do you have to do when you do the triangular solve? You've got to read the integers, don't you? And the reals. But wait. You go from I, you go from I plus 1. I just read those same integers in, darn it. Except for I itself. You don't have to read them in again. You know what they are. And they're sorted. These 2 sets are equal. They're sorted. You're just going to walk across the same integers. They're going to be identical. In fact, we would not have had to have stored them at all. If I know the second one is identical to the first one, why store both? That's called the supernodal method. What we can do is we can glue together, in the data structure, we could have, what we haven't for the project, we could have glued together these 2 columns into a single column, stored this way, in a little 2 by T matrix. And we could have stored the integers just once. And could have stored 2 columns there. And this can extend. What if I plus 2 and I plus 3? It just keeps getting bigger. You could have, say, 10 columns in here numerically. So this could be 100. Here we go. We could have 100 non-zeros in the first one, then 99 and 98, and then so forth, all the way down. Suppose we find 10 adjacent columns of L with all the same, where this property always holds. We just have to keep pruning away the first entry because it's lower triangular. Rather than, so I've got 1,000 numerical values to store, but look, I only have 100 integers to store. Okay. There's something else that can happen. And I've got maybe 30 seconds left. But the other thing that can happen is, let's just look at these 2 and imagine that in fact we do store all these integers. I don't have to look at these integers twice. What I can do instead is I could write a piece of code that operates on both of those loop iterations at the same time. Reads the integers once, and as it reads it in, I get an integer, I work on 2 numerical values, not just 1. So I can save, and when you work on 2 numerical values, you can save the gather scatter. What do you have to do with this? You have to gather from X, pull it in for that particular row. Look at X, if this is I, and this is also I. You've got to grab the ith entry from the X vector, do something to it, and write it back. And then what do you do here? Grab the same entry, do something to it, write it back. Well, wait. You just grabbed it, did, put. Grab, did, put. You only have to grab it once. Do 2 things, put. Gather scatter is very costly. So when you do this, you'll be able to speed the code up substantially, assuming MATLAB doesn't cause numerical cancellation. Okay, but we're going to assume it won't, and this is going to be the next project. What you're going to do is you're going to do this test. You'll know already that the MATLAB matrix is a Cholesky L. You'll walk through, do these tests, and if you find this to be true, you can lump two columns together. And you can go further, 3 or 4. But there's a point of diminishing returns. Probably 4 is what I'll have you do. Look ahead step maybe 2 or step 3, and then step 4, and then decide how big of a group you have. Is it size 1? Is it size 2, 3, or 4? Look ahead that far, and then do that as a unit. And what you'll find is you'll probably improve the speed for backslash over CSL solve by a factor of about 2. You should be about twice as fast because you cut out maybe more. If you really worked hard on this, you could make it maybe 10 times faster. But we're not going to do that. You should at least get a speed up of 2 by exploiting this. Okay, so we'll stop here, and I will pick up with this row count example on Monday. Thank you.